So let us start with the review session for today. Let us have the following. So write true if the statement is correct, is always correct, and then otherwise write false. Okay. So for number one, if an n by n matrix, if A is an n by n matrix and X is an n by 1 matrix such that the equation Ax equals 0 has only the trivial solution, then the matrix A is invertible. So for this, all you need to do is to recall the theorem, the big theorem that we had, the 7 equivalent statements. And this is one of those, or this is the two of those. You have this first statement in here. It is equivalent to the invertibility of your matrix A. So for this one, the answer is true. Okay. For number two, if A is a 3 by 3 matrix with determinant of A equals -4, then the determinant of 3A, this is equal to -12. So true or false. So for this is what you need to know. A, n by n matrix with determinant of A equals, yeah, so let's just write determinant A as itself. And then in here you have K, this is a scalar. Then the determinant of KA, this is equal to K to the n determinant of A. Okay? So if we use this, the determinant of 3A, since A is a 3 by 3 matrix, okay, determinant of 3A and A is a 3 by 3 matrix, this will be equal to the determinant of 3 raised to 3 times the determinant of A. Okay? And definitely this is not equal to 12. Well, of course, 3 to the 3, that's 3 times 3, that's 9 times 3, and then 27. And then determinant of A, it was given to be -4. So this is definitely not equal to -12. So the answer here is false. Okay? For number 3, if A, B, and C are n by n matrices such that AB equals AC, then B equals C. So if you go back to our discussion from before, I actually gave a particular example for this, and we found that this is false. Okay? And then for number 4, for any square matrix A, the matrix A minus A transpose is skew symmetric. So let us calculate that one. So we have a matrix A in here, a square matrix and A, and we want to know whether this guy here, A minus A transpose, is skew symmetric. And what do we need to show for skew symmetric matrices? So M, this is skew symmetric if and only if you have M transpose, this is -M. So we need to show this. Meaning, we have A minus A transpose, we need to get the transpose of that. Okay, and show that this is equal to negative of A minus A transpose. Now, the transpose operator, you can distribute it over the sum. So this is just A transpose minus A transpose transpose. But the transpose of the transpose, it's the original matrix. So this is just A transpose minus A. And then from here, you can factor out the negative, and you will have negative of A minus A transpose. And therefore, this is skew symmetric. A minus A transpose is skew symmetric. Therefore, this is true. Okay. Next, if A is a square matrix, then the determinant of A transpose, it is equal to the determinant of A squared. Okay. So for this, we'll just have, or we'll just need to use properties of determinants. Okay. So determinant of A transpose, this is equal to the determinant of A times determinant of A transpose. But the determinant of A transpose, that's the same as the determinant of A, correct? And therefore, again, applying the same property similar to what we did in here, this will become the determinant of A squared. So we have this guy here. Okay? So this is true. Okay? Questions? Okay. Now let us consider the linear system given by this. First, we want to find the reduced row echelon form of the augmented matrix associated to the linear system. And then second part, use your result in part 1 to find the general solution of the system. So we start with the augmented matrix. We have here 0, 1, negative 5, 1, and then 1, 2, negative 7, 0. And then we have 3, 2, negative 1, negative 4. So first step, we want a leading one in here. We can interchange rows 1 and 2. So for row 1, we will now have 1, 2, negative 7, 0. Row 2, we have 0, 1, negative 5, 1. Row 3, we copy 3, 2, negative 1, negative 4. And then this is a leading one. We want all the entries below it to be 0. So this is already 0. We just need to change the item in row 3. So we will have, we replace row 3 by row 3 minus 3 row 1. So we just need to copy row 1. 1, 2, negative 7, 0. We also just need to copy row 2. 0, 1, negative 5, 1. And then for row 3, we have 3 minus 3 times 1. That will become 0. And then here we have 2 minus 3 times 2. So that will be 2 minus 6. So we have negative 4. For this, we have negative 1 minus 3 times negative 7. So that will be negative 1 plus 21. So we'll get 20. And then lastly, in here, we just have -4. Okay? So we have this. And then in here, we want on the second row, we want a leading one here. It's already a leading one. So our next step is to make all the entries below that leading one, change them to 0. But we only have one entry in here. That's for -4. So let's just replace now row 3 by row 3 plus 4 row 2. So in here, we'll just copy row 1. So we have 1, 2, -7, 0. For row 2, we also need to copy that. 0, 1, -5, 1. Then for row 3, we do this. Row 3 plus 4, row 2. So this guy here is 0. The -4 plus 4 times 1, that will become 0. 20 plus 4 times -5, that becomes 20 minus 20. So this will become 0. And the third row, the last entry also here becomes 0. Okay? So now we have the 0 row here and there's no more row to consider. So we proceed to step 6. Remember the step 6? The backward phase of your Gauss-Jordan elimination method. So this is the leading one. This time we want, so we start from the bottom, but it's already 0 row. So we go up now. This is a leading one. We want the entries above this leading one, 0. So this guy here, we want this to be 0. So we apply the elementary row operation. We replace row 1 by row 1 minus 2, row 2. So this time we are changing row 1. So we have row 1 minus 2, row 2. This one here, it's 1 minus 0. That's just 1. In here, we have 2 minus 2 times 1. So we have 2 minus 2. That will become 0. In here, we have -7 minus 2 times -5. This will be -7 plus 10. So we will have +3. Then in here, you have 0 minus 2 times 1. So we'll just get -2. And then for the rest, we'll just copy 0, 1, -5, 1. And then here we have the 0 row. So this is the RREF. Okay? So this is the reduced row echelon form. So let me just write this. RREF. Okay? Number 2. So using 1, we have the following. We have x1 plus 3x3. This is equal to -2. And then we have x2 minus 5x3. This is equal to 1. Okay? Which means the general solution is we have x1. This is equal to -3t minus 2. X2. This is equal to 5t plus 1. And then x3. This is t, where t here is arbitrary. Okay? So this is the general solution. Okay? Now, let's have the following. So let A, B, C, and D be these matrices. First, we want to find 2B A transpose plus C cube. Then for number 2, we want to find X if X satisfies Cx equals 2D. Okay? So let's do number 1. Let's start with the BA. So this is your B. We have 4, 3, 0, negative 2, 1, negative 4, 6, 5. And then the A, this is A here. We have negative 1, 1, 2, 0, 3, negative 1, half, negative 1, 2. Okay? So let's see. We do the multiplication in here. We will have 4 times negative 1. That's negative 4. 3 times 2. That's plus 6. And then this is 0. And then we have negative 2 times negative 1. So we have plus 2. And then first row here, second column here, we have 4 times 1. That's 4. 3 times 0, that's 0. 0 times negative 1 half, that's 0 again. And then negative 2 times 2, that's negative 4. Now, second row, first column, 1 times negative 1, that's negative 1. 4 negative 4 times 2, that's minus 8. 6 times 3, that's 18. And then 5 times negative 1, that's negative 5. And then lastly, we have second row for second column. We have 1 times 1, that's 1. Negative 4 times 0, that's 0. 6 times negative 1 half, that's negative 3. And then 5 times 2, that's positive 10. So in here, if we simplify, we will have this is positive 8 minus 4, that's positive 4. 4 minus 4, that's 0. Here we have negative 1, negative 8 plus 18 minus 5. So we have here 18 minus 14. So that's again 4. And then in here you have 1 minus 3 plus 10. We have 8 for this part. Okay? So let us now get 2 times BA. Okay? So we have 2BA. This is simply 8, 8, 0, 16. Correct? And therefore, if we get the transpose of this, we need the transpose of this. This will become 8, 8, 0, 16. So this is to be a transpose. Now, let's do C cube. Okay, so C cube. Let's start with the C squared here. 1, 1, negative 1, 1 times quantity. We have 1, 1, negative 1, 1, 1, 1, negative 1, 1. So we start with 2. You can do this and this first, or you can do this and this, just like what I'm gonna do in this solution. So I'll do the last two matrices first before multiplying the third matrix. So I'll just copy. 1, 1, negative 1, 1. And for this guy here, we do the multiplication. We will have 1 times 1 plus 1 times negative 1. So that's minus 1. And then 1 times 1, that's again 1, plus 1 times 1 in here. So we have plus 1. Next, we have negative 1 times 1. We have negative 1. Plus 1 times negative 1. We have minus 1. And then lastly, we have negative 1 times 1. We have negative 1 there. Plus 1 times 1. So plus 1 in here. Okay? So if you simplify this, we will have 1, 1, negative 1, 1 on the left factor here. For the right factor, we will get 0, 2, negative 2, 0. Okay? So, if we multiply the two guys here, we will just have 1 times 0, that's 0, plus 1 times negative 2, that's negative 2. And then 1 times 2, that's 2, plus 1 times 0, that's 0. Then here, negative 1 times 0, that's 0, plus 1 times negative 2. We'll get negative 2 here. And then negative 1 times 2, that's negative 2, plus 1 times 0. So we have this as our C cube. Therefore, we have 2BA transpose plus C cube. We just need to add this guy here and this guy here. So we will have 8 plus negative 2, that's 6. 8 plus 2, that's 10. 0 minus 2, that's negative 2. 16 minus 2, that's 14. So this is the final answer for number 1. Okay, so now let's get letter number 2. So we want to find Cx equals 2D. We want to find x if Cx equals 2D. So in here, C, this is a square matrix, okay? So what we can do is to know what the determinant of C is. If the determinant of this C is not equal to 0, then the matrix C is invertible. Okay? And if it is invertible, then we can simplify this expression here, this equation here, in a sense. Okay? So the determinant of C, this is just 2 by 2. This is just 1 times 1 minus. So 1 times 1 in here minus negative 1 times 1. And this is equal to 2. Okay? That's equal to 2. Which means that C is invertible. C is invertible. Okay? Therefore, Cx equals 2D. You can now isolate x. So you will have x equals C inverse times 2D. And your 2 here, it's just a scalar, it can go out. So you'll just have 2 times C inverse times D. Okay? Now, let's find C inverse. We know that the determinant of C, this is equal to 2. So let's continue up here. Therefore, C inverse, this is equal to 1 over the determinant of C, which is just 2, times, what do? We interchange 1 and 1, but it's still 1 and 1 in here. And then we negate. We negate this, we negate this. So this is 1, this is negative 1. Okay? Now we can do the multiplication of 1/2 over these entries here. Okay, but I'll retain this 1/2 because as you can see in here, I will multiply this guy here anyway with 2 or by 2. Okay, or maybe you can think of this from here. You will have 2C inverse. This is simply 1, negative 1, 1, 1. And therefore, this 2C inverse here, it's just this matrix. Therefore, you'll just have 2C inverse times D. So we have 1, negative 1, 1, 1 times the matrix D. We have 1, 4, 3, negative 5, 2, 6. So this is equal to, we have here 1 times 1, that's 1, times, plus negative 1 times negative 5. So that's plus 5. Then 1 times 4, that's 4. Negative 1 plus times 2, that's 4 minus 2. And then in here you have 3 minus 6. And then on the lower row here, you have 1 times 1 plus 1 times negative 5. So all you need to do is to add the entries in here. So you will have here 1 minus 5, 4 plus 2, 3 plus 6. And therefore, if you simplify this, you will have 6, 2, negative 3, negative 4, 6, 9. So this is the final answer. Now let us have this. Use inversion algorithm to find the inverse of this matrix. And then after finding the inverse, find the adjoint of the matrix N. So for the inverse, we copy the matrix on the left. We have 0, 1, negative 4, 1, 3, negative 4, 2, 5, negative 3, and we augment the identity matrix in here, 1, 0, 0, 0, 1, 0, 0, 0, 1. Then we find the reduced row echelon form of this new 3 by 6 matrix. So first, we can interchange rows 2 and 1 because this is 0, this is 1, so we want a leading 1. So row 1 interchange with row 2. So for row 1 now, we will have 1, 3, negative 4. Then the other side here, it's 0, 1, 0. Then for row 2, we have 0, 1, negative 4. On the other side, we have 1, 0, 0. For row 3, we have 2, 5, negative 3. And then we have 0, 0, 1. And then this is now a leading one. This is 0. We want this one to be 0. So we do row 3 minus 2 row 1. So row 1 and row 2, we just copy it. So we will have 1, 3, negative 4, 0, 1, negative 4 on this side. On the other side, I have 0, 1, 0, 1, 0, 0. For the third row, we have 2 minus 2. That will become 0. 5 minus 2 times 3. So 5 minus 2 times 3. So 5 minus 6, that's negative 1. Then negative 3 minus 2 times negative 4, that will be negative 3 plus 8. Correct? Negative 3 plus 8. So that will become 5. And then for the one here, the third row here, or on this side, we have 0 minus 0. That's still 0. 0 minus 2 times 1, it's negative 2. 1 minus 0, that's 1. Okay? Now, go back to step 1. This is leading 1. So we now jump to step 4. We want this to be 0. Okay? So this guy here, what we can do is to add row 1 plus row, row 2 plus row 3. So row 2 plus row 3. Okay? And then we have here row 1 plus row 3. So 0 plus 0, that's still 0. Uh, I am changing row 3 in here. So just to be consistent with my notation, I will interchange these two. So row 3 plus row 2. So I am changing row 3. I am using row 2. Okay? So I have here 0 plus 0. The negative 1 plus 1, that's 0 now. 5 minus 4. So that becomes 1. And then on the other side in here, we will have 0 plus 1. That's just 1. And then negative 2 plus 0. That's still negative 2. The last one, that's still 1. Okay? And then we just copy the first row and the second row. So we have here 1, 3, negative 4, 0, 1, negative 4. On the other side, I have 0, 1, 0, 1, 0, 0. Okay? So now in here on the third row, this is now, well, on this side here, this is a triangular matrix. So now we start with step 6. We now go the backward, we now do the backward phase. So this is a leading one. We want this to be 0 as well as this guy here. So here we will have, we replace row 1 by row 1 plus row 4 row 3. Row 2, we do the same thing. So row 2 plus 4 row 3. So if we do that, we have row 1 plus 4 row 3. So 1 plus 0, that's still 1. 3 plus 0, that's still 3. Negative 4 plus 4 in here, this becomes 0. On the other side, we have 0 plus 4 times 1, that's 4. 1 plus 4 times negative 2, so 1 plus, or 1 minus 8, that's minus 7. Then 0 plus 4, so we have the 4 in here. For the second row, we have row 2 plus 4 row 3. We have 0 plus 0, that's still 0. 1 plus 0, that's still 1. Negative 4 plus 4 times 1, that becomes 0. In here, we have 1 plus 4 times 1, that becomes 5. Then 0 plus 4 times negative 2, so we have negative 8. Then 0 plus 4 in here. Then for the row 3, we just copy 0, 0, 1, 1, negative 2, 1. Okay? Then we now go up. For this leading one, we want to make this 0. So we do row 1 minus 3 row 2. So if we do that, this is 1 minus 0, that's 1. 3 minus 3 times 1, that becomes 0. And then 0 plus or minus 0 here, you have that 0. On this side, we have 4 minus 3 times 5. So 4 minus 15, that's minus 11. Then here, minus 7 minus 3 times negative 8. So what's that? Minus 7 plus 24. So 24 minus 7, that's 17. Then here you have 4 minus 3 times 4. So this is 4 minus 12. And 4 minus 12, that's minus 8. Then we copy the second and third row. So 0, 1, 0, 0, 0, 1. The other side, we have 5, negative 8, 4. Then 1, negative 2, 1. Okay? So which means this guy here, this will be your inverse. This is identity matrix on this side. So this is the inverse. Okay? So let us write that. So it's negative. Let us write that. So we have n inverse. Therefore, n inverse, this is the matrix negative 11, 17, negative 8, 5, negative 8, 4, 1, negative 2, 1. Okay? Now, what about the adjoint of n? For the adjoint, recall we can use the following. The adjoint of n, this is equal to the determinant of n times n inverse. So all we need to do is to find the determinant of n here. Okay? So for that, we have determinant of n. You have 0, 1, negative 4, 1, 3, negative 4. 2, 5, negative 3. So calculate the determinant. So we have here 0 times 3 times negative 3, that's still 0. And then here 1 negative 4 times 2, that's negative 8. And then negative 4 times 5 times 1. So that's negative 20. And then minus, okay, minus going up, 2 times 3 times negative 4. This is minus 24. And then 5 times negative 4 times 0, that's just 0. And then plus, actually it's minus. So we have here minus 3 times 1 times 1. So that's minus 3. Okay? So if we calculate this, as you can see, we have here minus 28 minus, in here you have minus 24 minus 3, that's minus 27. So this is just negative 1, which means this adjoint, it's just the negative of n inverse. So let me just write the adjoint itself. We have here 11, negative 17, 8, negative 5, 8, negative 4, negative 1, 2, negative 1. So this is the adjoint. Again, taking into consideration this determinant here. Okay? Next problem. We have this. So we have a linear system given by this. In here, I wrote the matrix of coefficients. Okay? So it's this guy here. So the problem is we want to find the determinant of A. Okay? And then for number 2, we use Cramer's rule to find the value of the variable x2 that will solve the system without solving for the other variables. Okay. So for number 1, let's start with the determinant of A. So this column here, okay, it has many zeros. So um, I will expand. Okay, I will do the expansion along this along this fourth column, and then as you can see, 0 times this, 0 times whatever, and then we just have the 1 in here. And then the other guy, again, it's 0. So basically, we just have to do this part here. So this is equal to 1 times negative 1. So this is 1, 4, 2, 4, and then this one here. This n3 is at 3, 4. So the exponent of negative 1, it's 3 plus 4. And then we delete this matrix here. This row here and this column here, which means that we just need the determinant of 4, 1, 0, 0, 1, negative 3, 4, 2, negative 1. Okay. And then to get the determinant of this, let us use the method for finding determinant of 3 by 3. Okay. So you copy this matrix, you augment the first two columns. That method is the method I used in solving this. Okay, it's the same method, except that I did not show you the the first column and second column augmented into this matrix. But it's that method. Okay. Yeah, for the sake of recalling the method, I'll 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 augment the first two columns here and then do that multiplication going down and going up, etc. So let's do that. We have, let me put the computation somewhere here. So I have 4, 1, 0, 0, 1, 3, or negative 3, 4, 2, negative 1, augment the first two column, 4, 0, 4, 1, 1, 2. So we have this guy here, then we have this guy here, and then this guy here. So we'll have negative 4, this is negative 12, and this is 0. Correct? And then for the going up, this guy here, this guy here, and this guy here. So this is 0. 4 times, there's negative there, don't forget. So 4 times negative 3 times 2, that's negative 24. And then this is 0 again. Which means the determinant now it's equal to, here we have 1 times negative 1. So we have negative of what? We have here negative 4 minus 12 minus. And then up here we have minus 24. So what is this? This is equal to negative of negative 16 plus 24. So this is equal to negative 8. Okay? So the determinant of A, it's equal to negative 8. Questions? Now, for number 2, we want to solve for the variable x2 using Cramer's rule. So what we're going to do is to replace this second column here by the constant column in here. Okay? So this is what we will have. So we have A2. This is equal to the matrix. So per column, I'll do per column here. So 4, 0, 10, 4. Then this column is replaced by this 0, 2, negative 1, 1. Then for this, we will have 0, negative 3, negative 2, negative 1. And then we have 0, 0, 1, 0. Okay? And then what's next? We find the determinant of A2. Okay? So again, we are doing now number 2. So we want to find the determinant of A2, but notice we can still use column 4 for our cofactor expansion. Okay? So if we do that, we now have, so separator, we have determinant of A2. We do, again, expansion along column 4. So almost similar to the one before. So we have here 1 times negative 1 raised to 3 plus 4. But take note, the matrix that we are going to multiply is now different because the second column changed. So be sure that you have the correct matrix. So again, I am expanding along this column. I am at this entry. So this guy here is deleted and also this guy here is deleted. Okay? So the submatrix left, it's this guy. So 4, 0, 0. And then we have 0, 2, negative 3. Then here 4, 1, negative 1. 4, 1, negative 1. Okay? Questions so far? Now for this, of course, this guy here, again, it's negative 1. But for this, look, this is a 3 by 3 matrix. You can do the method that we used from the previous. Okay? But we can also do cofactor expansion. This time, we do the cofactor expansion along the first row. The reason is, well, this is just 4, and then we have here 2, we have here 0 and 0. Okay? So we can do the cofactor expansion along this row. And then we just have this entry. So this is now equal to. So this guy, again, it's negative. Okay? And then we have the 4 in here. And then we have negative 1 raised to. This guy here, it's the 1, 1 entry. So the exponent, it's just 1 plus 1. And then we delete this row, we delete this column. So we are now getting the determinant of this. 2, negative 3, 1, negative 1. And this is just a 2 by 2 matrix, so we can easily get the determinant of that. Negative 1 raised to 1 plus 1, this is positive 1. So we'll just have negative 4 times. In here, you have 2 times negative 1, that's negative 2, minus 1 times negative 3, that's negative 3. So this is just negative 4. Okay? Therefore, we now have our x2. Therefore, x2, this is the determinant of A2 divided by determinant of A. Determinant of A2, that's negative 4, while the determinant of A, it was negative 8 here. So we have negative 8, and therefore x2, it's 1/2. Okay? Questions? Next problem. Okay. Now, let A, so this is proving, let A and B be M by n matrices. Show that if A and B have the same reduced row echelon form, then A and B are row equivalent. Okay? So what is this row equivalent again? So two matrices A and B are said to be row equivalent if A can be derived from B by applying a sequence of elementary row operations on B. Okay? So this means that we can write A as a product of B times some elementary matrices. Okay? Or we can write B as a product of A times some elementary matrices. Okay? So let's have the proof. So let A and B be M by N matrices such that they have the same reduced row echelon form. The same reduced row echelon form. Say, let's give a name for the reduced row echelon form. Let's say it's R. Okay. Then, okay. Then, these are here, the reduced row echelon form. Okay. This is equal to some A sub I, A sub I minus 1, dot, 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 A sub 2, A sub 1, A. Okay. So R is a product of A sub I minus 1 until A sub 2 times A sub 1 times A. Okay. Where here, let me write it here, where A sub I minus 1 until you have A sub 2 and A sub 1. Okay. These are elementary matrices. Elementary matrices. Okay. Similarly, your R can also be written in terms of B. Okay. Let's say Bj minus 1. You have B2, B1 times B. So if you multiply all of this, you will get your R also. Okay? Because they have the same reduced row echelon form. Okay? If this is the reduced row echelon form, you will find this matrices B. You will also find this matrices A's here. So I'll just extend this. Okay? We have here Bj minus 1, B2, and B1. Okay? Where these matrices here are elementary matrices. Okay? And then what we're going to do is to apply the property. They are equal, okay? And elementary matrices are invertible, okay? Elementary matrices are invertible. You'll just have to multiply by the inverse, okay? So in here, we will have, let's start with this guy here, AI, AI minus 1, A2, A1A. This is equal to BJ, BJ minus 1, B2, B1, B. Okay? They are equal because they have the same um, reduced row echelon form. Since elementary matrices are invertible, elementary matrices are invertible, we can just multiply by the inverse, okay, of the AI minus 1 until A1, okay? Since elementary matrices are invertible and their inverses, okay, are also elementary matrices, their inverses are also elementary matrices, we have the following. So you multiply, so look at this. I'll multiply AI inverse in here. I will multiply AI inverse in here. So AI inverse will cancel AI. It becomes the identity matrix. And then next, I'll multiply AI in AI minus 1 inverse in here. And then I'll multiply the AI minus 1 inverse also in here. Then again, this guy here will cancel, etc. So you do that. You do that, and you will obtain, you will get A. This is equal to A1 inverse, A2 inverse, until you have AI minus 1 inverse, and then AI inverse. And then you have your BJ minus 1 until B2, and then B1, and then B. Okay? And that's it. You can derive A, okay? You can derive A by applying elementary row operations on B. Okay? Or A is just a product of elementary matrices times B. Okay? And that's precisely what we want to prove. So A is a product of elementary matrices, elementary matrices, and B. Okay? So A is a product of elementary matrices and B, and therefore A is row equivalent to B. A is row equivalent to B. And that's the end of the proof. Okay?